For Chapter 19, we're going to start by looking at a series of balancing chemical reactions where we have to worry about not just atoms, like we did in 1211, but also the electrons that are present and how we take into account how many electrons certain atoms gain and lose. We'll then follow up by looking at some problems related to voltaic cell potentials, and then finally we'll look at how we can relate that to free energy. So let's start with this first question. We want to balance the following reaction in acidic solution. So the first thing we need to do is, just like from 1211, is assign our oxidation numbers, because we need to know what's gaining and what's losing electrons. So to do that, we're going to start here. Oxygen, we know, has an oxidation number of -2. We have 4 oxygens. That gives us a -8 overall. And because this is a -1 charge, we want to get to -1. To get from -8 to -1, chlorine has to have an oxidation number of +7. Then here, Cl is by itself, and it's just a -1 charge, so it needs a -1 oxidation number. Then we come over here. Oxygen is still -2. We have 3 of them this time, so this is -6. So to balance that, we need a +5, which gets us to our -1 charge here. And then here, chlorine is by itself, and it has no charge, so chlorine is just a 0 here. So if we look, we now need to divide this up into our half reactions. So we notice that ClO4- here, this chlorine goes from +7 to +5 here in ClO3-. So it is gaining electrons for that one. So let's do that one first. So we have ClO4- aqueous. And when you're writing, you should write these closer together. And then reacts, it forms ClO3-. So to start, we need to balance all our non-oxygen and hydrogen atoms, but our chlorine's already balanced. So we're done with that step without having to do any additional work. Then we need to balance our oxygens next. So I'm going to add 1 water. That's because my 1 water is able to add 1 oxygen, which gets me to 4 oxygens on both sides. We now have extra hydrogens on our product side, so I need to add 2 hydrogens over here, so 2H+. From there, we're now balanced with all of our atoms. Our hydrogens, oxygens, and the non-hydrogen oxygen atoms are all balanced. So now I need to balance the electrons. So we know that chlorine here is in a +7 state, and it's a +5 state on the other side. So we're gaining electrons. That means our electrons are going to act as a reactant because we have more at the end than we started with. So I'm going to put 2 electrons over here on the reactant side. Now let's balance our other one. So we have Cl- is going to go towards chlorine gas. So in terms of atoms, we're not good on the chlorine yet because we have 2 chlorines on the product side but 1 on the reactant side. So I'm going to put a 2 here. And now we have 2 chlorines on both sides. There are no oxygens and hydrogens, so we don't have to worry about adding waters or H+. And now we need to finish with the electrons. Each chlorine is going from -1 to 0, so it's losing 1 electron, and there are 2 chlorines doing that. So we lose a total of 2 electrons here, and when we lose them, that means they're going to act as a product. So we're going to have +2 electrons on this side. Now we checked our 2 half reactions to make sure they have the same number of electrons. If they don't, we have to multiply everything in the reaction by some number to get the electrons equal, because we won't have any electrons showing up in the final balanced chemical equation. But for this one, we're already balanced. We have 2 electrons on top, 2 on the bottom reaction. That means we're good to go. So now we can just add these 2 together. And so that's where we take all our reactants, put them together, take all our products, put them together, and anytime you have something that appears in both the reactant and the product side, they're able to cancel out. So for example, we have 2 electrons in the reactants, 2 in the products. So none of them are going to show up at the end. Everything else, though, we don't have any things that match exactly, so everything else we're just going to write out. So this reaction, we have 2H+ aqueous plus ClO4- aqueous plus 2Cl- aqueous. And this is going to react to form ClO3- aqueous plus water liquid plus chlorine gas. And if you check and you add all your atoms up, you'll get the same things. So for example, we have 3 chlorines on both sides. We have 4 oxygens on both sides. We have 2 hydrogens on both sides. And because we're balancing an acidic solution also, we didn't have to do anything else extra with OH-. So now let's look at a problem where that's not true, where it's a basic solution and we have to do something with that. This is our second reaction. So here, we still start to say all the steps for basic solution balancing are the same as hydrogen up until the step where we add the H+. We have 1 more step to do that. But nothing else actually changes. So still follow all the basic steps. So assigning oxidation states, oxygen's a -2, manganese is a +7, Br- is a -1, oxygen is a -2 here, manganese is a +4, oxygen is a -2 here, and then our bromine is a +5. So we have to split it into the 2 reactions. So I'm going to start with my manganese reaction where it went from +7 to +4, which means it's gaining 3 electrons there. So we have MnO4 minus aqueous reacts to form MnO2 solid. Our manganese is already balanced, so we don't have to worry about it, but our oxygen isn't. So I need to add 2 waters on this side. And just for purpose of space, I'm not going to be writing phases with my waters and my hydrogens and my OH minuses. I'm going to wait to do that at the end. Don't forget to do that, though, before the end of your problem. I'm just doing that because there's literally not enough room on this line. So now we've added our waters. The next thing we need to do is we need to balance our hydrogens. So here we have 4. So I need to put 4 on this side. So 4H plus over here. Now, if we were doing just basic solution, acidic solution, we could move on to electrons, but we're doing a basic solution. So I can't have H pluses sitting there. So I need to add 4 OH minuses here to get rid of these. But when I add 4 OH minus, those are new atoms I'm adding. So I have to add the same to the other side. So we've got to keep this balanced. So I have 4 OH minus here. These combine to form 4 water molecules, which is good because we don't want to have any H plus sitting in solution. If it's basic, we're going to have mostly OH minus, so that's what we should see in our reaction. We can also tell now that we have 4 waters on the reactant side, but 2 on the product side. So I'm going to get rid of these, and I'm going to get rid of 2 of these. So we only have 2 waters now on our reactant side and none on our product side. So now we've balanced all of the atoms. So the next thing we need to do is balance the electrons. So manganese, we have 1 manganese going from +7 to +4. That means that it is gaining 3 electrons. So the electrons need to be on my reactant side. And I'm going to have it right here, 3 electrons. So now this half reaction is good to go. Let's look at the bromine next. We have Br minus aqueous goes to BrO3 minus aqueous. Bromines are already good. Now to get the hot oxygens, I'm going to add 3 waters over here. We're then going to have to add our 6 hydrogens over here. We can't just add 6 hydrogens, though, because we're not going to be okay with that in basic solution. So I'm going to add 6 OH minuses, which is going to put 6 OH minuses on the other side. These combine to form 6 waters. And now we have them on both the reactant and product side. So I'm going to get rid of my 3 reactant waters. This is going to become 3 waters on my product side. Finally, we need to deal with the electrons. And so bromine went from a -1 to a +5, so it lost 6 electrons. And it lost them, so they're going to show up on my product side. Now you'll notice this time we have 6 electrons in our 1/2 reaction and 3 in the other. We have to get them to the same number. So our lowest common multiple with 6 and 3 is just going to be 6. So I don't have to change the second reaction at all, but I need to change my top reaction by doubling the number of electrons present. So we'll come up with the equation 6 electrons plus 4 waters plus 2 MnO4 minus aqueous goes to 2 MnO2 solid plus 8 OH minus. And then just because there's some slash marks to make sure it's clear, I'm going to go ahead and rewrite the other equation as well before we add them together. Even though I'm not changing it, you don't actually have to do that, but I'm going to make it easier for me. This forms BrO3 minus aqueous plus 3 waters plus 6 electrons. So the first thing to check when we're adding them is that the electrons are the same, which they are. So these are going to go away. Next, I'll look and see I've got 4 waters on the reactant side, but 3 on the product side. So I'm not going to have any waters on the product side. And this is just going to go to 1. MnO4 minus doesn't show up on other sides, but OH minus does. So our 6 reactant OH minuses, we're not going to see those. And this 8 is going to become a 2 OH minus over here. And then all of our like terms have been combined. So now I'm actually going to write down my full equation. So we have 1 water, so we'll just put H2O. H2O is a liquid, plus 2 MnO4 minus aqueous, plus Br minus aqueous is going to react to form our 2 MnO2 solid plus 2 OH minus aqueous plus BrO3 minus aqueous. So as you can see, this does take a little bit of time sometime with the reactions, but it's very systematic. Just I suggest doing it in the same order I'm doing it, and that helps make sure that you keep yourself structured. And just try not to get lost too much in this, as they can take a little while. But they're very systematic. There aren't really any tricky steps per se. There aren't exceptions inside of this. This is always the same systematic process. Go through each one, you'll be good. So now that we've done some balanced chemical equations, let's look at doing some more with the actual cells we can build out of these. So this asks us to draw a voltaic cell for the reaction of nickel solid plus copper 2 plus goes to nickel 2 plus plus copper solid. So I'm not going to be picky about exactly how you draw it, but I'm going to draw a set of 2 beakers. And then now inside these beakers, I know I have to have electrodes. We've got our voltaic cell. Okay, so I'm not very good at drawing something. I'm not going to be picky about this. This should be more rectangular, but this little drawing pad is really hard to draw on. Okay, let's see if I can do it this time. Come on. Oh, no, that's really curvy. I tried. Yeah, this electrode would not survive well, so I'm glad that I don't have this in reality. But yeah, I will not be picky on how you draw this thing. And here's my salt bridge. Don't forget that. So now I need to identify where things are going to be, and I'm going to label them. So I'm going to put my anode on my left and my cathode on my right. So we know that it's the nickel that's losing the electrons because I can assign these real quick. 0, plus 2, 0. So if nickel's going 0 to plus 2, it's what's losing electrons. That means this is going to be my nickel solid. My nickel 2 plus is going to have to be in the same beaker. Then my electrons are going to, well, let's just label these first. So my cathode is going to be my copper solid. Then I have my copper 2 plus here. We then know the electrons are going to have to flow from the nickel to the copper. That means my electrons are going to flow up and through this wire. Remember, they go through the wire, not through the salt bridge. And so this is enough labeling. I now have a voltaic cell. Let's look up at a follow-up question to this, though. So for that cell I just wrote, let's see what the potential would be if the copper 2 plus had a concentration of 0.2 molar and the nickel 2 plus had a concentration of 0.8 molar. So we're going to start by finding the standard cell potential first. So this problem will actually let us practice both, because we need to have standard cell potential to find our non-standard potential. So remember that E naught cell is just going to be E cathode minus E anode. So if we look up the value for our cathode, we're going to get that we're going to have 0.34 volts is what we get for the copper 2 plus to copper reaction. We're then going to subtract our anode, and our anode is negative 0.23 volts. If I combine those, I'm going to get a standard potential of 0.57 volts. Now we've got to plug it into our equation that E cell equals E cell naught minus 0.0592 volts over, and our N is going to be 2 here, and then times the log of Q. So I'm going to do Q right below this to show you what I got for Q. So Q is equal to, for our balanced chemical equation, nickel 2 plus over copper 2 plus. That's because we don't put our solids in our Q, so we don't have the nickel solid or copper solid, and Q is just products over reactants. So nickel 2 plus was on the product side, copper 2 plus was on the reactant side. So then I'm going to plug in 0.800 molar divided by 0.200 molar. And then also this 0.57 volts is what goes right here. So when I plug all those numbers in my calculator, I'm going to get that my E cell is equal to 0.55 volts. And if we were asked also, we could say that this cell is still going to be spontaneous. So there we go. So let's look at one more question. We want to know how to calculate a delta G reaction from tabulated electron potentials. So for this reaction, I'm going to need to start by, again, finding my E standard. E cell naught, and we know we're working with the standard potential because of this circle right here. This means we want delta G at standard conditions, so we can find E cell at standard conditions, and we are good to go. And we don't have to worry about anything else. You're still going to want E cell, but you'd have to do more to this if this was just delta G. So we're looking for delta G naught. So our E cell, when we look it up, so bromine is going from 0 to -1, and iodine is going from, the iodide ion is going from -1 to 0. So that means we know that our bromine is going to be what's gaining electrons, and our iodine is what is losing electrons. So when I look up my cell potentials, for my cathode I get 1.09 volts, then for my anode I get 0.54 volts. We're going to combine these, and we get an E cell standard of 0.55 volts. We'll then plug in our equation that delta G naught is going to be equal to negative N Faraday's constant times E naught cell. So we plug these in. This is an electron transfer of 2 electrons because each bromine went from 0 to -1, but there are 2 bromines, and each iodide went from -1 to 0, but there are 2 of them as well. We then plug in our constant, which is going to be 96,500, and then our E cell of 0.55 volts. When we plug all of this in, we're going to get a value of negative 106,000. What's important to remember is this is going to be in joules per mole, and that's because of the unit on Faraday's constant, which was joules per volt to atoms moles. So the volts canceled from the E cell, and so I'll just show the work for that. So unit-wise, we had... Oh, right, we're just going to have joules. Yeah, we're okay with that. So Faraday's constant is joules per volt mole of electrons. So yeah, so that's why we're going to be in joules and not kilojoules yet. So you could leave it in that if the problem doesn't ask for a specific unit, but I like to report my delta G's in kilojoules. So we're good. And I didn't have this mole here either, because we dealt with that already. That was the moles here and moles of electrons here. So we have negative 106 kilojoules. It's going to be our delta G value.